Welcome to my YouTube channel scientific_math. Today topic is the derivative as a function. Learning objectives. Define the derivative function of a given function. Graph a derivative function from the graph of a given function. State the connection between derivatives and continuity. Describe three conditions for when a function does not have a derivative. Derivative function. The derivative function gives the derivative of a function at each point in the domain of the original function for which the derivative is defined. Definition. Let f be a function. The derivative function denoted by f prime is the function whose domain consists of all those values of x such that the following limit exists. A function f of x is said to be differentiable at a point a if f prime of a exists. Generally, a function is said to be differentiable on S if it is differentiable at every point in an open set, and a differentiable function is one in which f prime of x exists on its domain. It means the derivative of the function is exist on the given domain of the function. Okay, so here we have an example. Find the derivative of f of x, that is under root of x. So we find the derivative of this function by using a definition, and here we know that the definition of the derivative is f prime of x is equal to limit as h approaches to 0 f of x plus h minus f of x divided by h. We apply this definition on given function. So after applying the definition, we have this expression, and we simplify this expression by multiplying the numerator with the sign positive. Here we have a multiply and divide this expression with this term, and after simplification we get this one, and h will cancel out this h, and we get this expression, and we apply the limit as h approaches to 0. This will be 0, and under root x plus under root x will be 2 under root x. Okay, so this is the derivative of a given function f of x, that is given function f of x that is equal to under root of x, and the derivative of this function we have find using the definition which is 1 divided by 2 under root of x. Graphing a derivative. We can use the graphs to understand the relationship between function and derivative function. Here we have a graph of our function, that is under root x, and this is the graph of a derivative function, that is 1 divided by 2 under root x. Okay, first we notice that f of x is increasing. First we notice that the function f of x is increasing for all values of x in its domain. Furthermore, as x is increasing, the slope of the tangent line to f of x are decreasing. We can see here the slope of the tangent line. This is the slope of the tangent line is decreasing as x is increasing, and also the derivative of the function is decreasing as x is increasing. This is the derivative of the function at each point. We expect to see a corresponding relation decrease in f prime of x. Here we see that the derivative of the function, is also decreasing as x is increasing. So this is the relationship between the derivative function and the function. We also observe that and the derivative of the function at 0 at x is equal to 0, and that is infinite. Here we also see that the slope of the as limit x approaches to positive, this is the right hand limit. As x approaches to 0, f prime of x which is equal to positive infinity, and this mean the slope of the tangent line that is infinite. Okay, at x is equal to 0. So corresponding to a vertical tangent to f of x at 0, at this point at x is equal to 0, the function has a tangent line. Okay, the function has a tangent line at this point, and the slope of the tangent is infinite. When the function has a vertical tangent line, then the function is not differentiable at that point on which the function has a vertical tangent. Okay, so this is the relationship between derivative function and given function when the function is increasing. Here we see when the function is increasing, the derivative of the function is decreasing as x is increasing. Okay, and at x is equal to 0, the function has a vertical tangent, and at that point the derivative of the function is not exist. Now we write a Matlab code to graph a derivative function and a given function. Matlab code. This is the initial command clc clear all and close all to clear screen and clear data, save data, and close all figures for. Okay, here is the format short command, and x is equal to linspace 0 to 3. This is the domain of x, and linearly space command we use for linearly space between 0 and 3, and this will give us 100 points between 0 and 3. Again, for capital X, linearly space command 0 to 4, and h is equal to 0 0.0001. Here we have this is increment. Okay, and this is the given function sqrt, and we f is equal to use f of x. We find the value of the function at each x, and this command for white color, for setting the figure color white, and now we use for loop for I is equal to 1 to length of x, and this is the derivative function. This will give us a derivative function, and this is the slope of the tangent line at each point, and this is the equation of a tangent line. Okay, so then we plot our derivative function, x versus derivative function, and x versus a given function, that is f of x or under root x. Okay, and x versus derivative function, our derivative function is 2 under root of x. We find the derivative function at by using this formula, by using definition of a derivative. So then we plot our given function x versus given function and x versus derivative function, and then the tangent line x versus, this is the capital X for length for a tangent line, and this will plot our tangent line at each point with green color, and this will plot a red circle on a graph of the function. This is the red circle on graph of the function at each point. Okay, so this command is used to plot x-axis like that. This is the x-axis for -1 to 4, and y-axis 0 0 on this on x-axis with black color, and this command used to plot y-axis. Okay, and at y-axis x is 0, and y limit of y is -1 to 5. Okay, so this is again black color, and the width of the line is 2. The width of the line, this is the width and this is the width of the line, is 2. Okay, this line indicate the given function, and this line indicate the derivative function, and green line indicate the tangent at each point, and this is the derivative of the function. This red circle indicate the derivative at each point, or the slope of the secant line at each point, because we know that derivative is equal to slope of the tangent line. Okay, so the legend command is used to define a function, derivative function, tangent at each point, and this is our legend command. Okay, so this is the x limit. This command is used to set the x limit, and this is y limit. This is our x limit -2 to 5. Here we have a 5, and y limit -2 to, this is -2 to 5. Okay, then we use a command and draw now, and we end our for loop. Okay, so this is the Matlab code to plot a function and derivative function and a given function. Okay, so we check this function, and as x is increasing, the tangent, the slope of the tangent line is decreasing. This is the behavior of a tangent line at each point, and this is the derivative of the function. We also see that as x is increasing, this tangent, the slope of the tangent line is decreasing, and the derivative is also decreasing. And this is the graph of a derivative function, and this is the graph of a given function. As x is increasing, the function is increasing as x is increasing, but the derivative of the function is decreasing. We also see that the derivative of the function is positive as x is increasing. As x is increasing, the function is increasing, and the derivative of the function, that is 1 by under root 2, which is 1 by under root 1 divided by 2 under root x, which is positive for all values of x. As x is increasing from 0 to we have used limit in 0 to 3. This is our domain for, or the limit for x. As x is increasing from 0 to 3, and the derivative is positive, and the slope of the tangent line is decreasing as x is increasing. We also see here the derivative of the function is also decreasing when x is increasing. Again we see and this the behavior of our given function, that is as x is increasing, the slope of the tangent line is decreasing, and the derivative of the function is also decreasing. This is the derivative of the function, decreasing 0.3 and so on. This is decreasing as x is increasing. Example: find the derivative of a given function, that is f of x is equal to x square minus 2x, and the derivative of this function is f prime of x is equal to 2x minus 2. And this is the graph of a given function, which is f of x is equal to x square minus 2x, and this is the graph of a derivative function, that is 2x minus 2. Okay, so observe that f of x is decreasing for x less than 1, and this is we can see, and this is for this one, x is less than 1 and x is greater than 1 over here. Okay, so we can see that the function is decreasing for x less than 1, and for the these same values of x, the derivative of the function is also negative, this which is also decreasing. We can see that the derivative of the function for x less than 1, that is negative. Okay, and for the value of x greater than 1, the function f of x is increasing and the derivative of the function is positive. Here we can see that the function for x greater than 1, the function is increasing, and the derivative of the function is positive for x greater than 1. So also for f of x has a horizontal tangent at x is equal to 1, and the derivative of the function at 1, which is 0. Here we have a function the derivative of the function f prime of x which is 2x minus 2. If we put x is equal to 1, 2 minus 2, which is 0, and at this point we will see the derivative in the tangent at x is equal to 1 will be horizontal. So we see the tangent at each point of the function. Here we can see that the derivative of the function is a negative from x less than 1, and the tangent line is also the slope of the tangent line is also negative over here, and we will see when x greater than 1, the derivative of the function is positive and the slope of the tangent is also positive. At x is equal to 1, at this point the derivative of the function will be 0 and the tangent will be horizontal at this point. This is the derivative is 0. Okay, so now the derivative is positive, the slope of the tangent line is positive for x greater than 1. So this is the relationship between a graph of a function and the derivative of a function. Differentiability and continuity. We consider the relationship between the differentiability and continuity. We will see that if a function is differentiable at a point, it must be continuous, and there, however, a function that is continuous at a point needs not to be differentiable at that point. In fact, a function may be continuous at a point and fail to be differentiable at the point for one of several reasons. Differentiability implies continuity. This means if a function is differentiable, then the function will also continuous. Let f of x be a function and a be a point on its domain, a be the points on its domain. If f of x is differentiable at a, then the function f is continuous at a. So we will prove this if a given function is differentiable at a given point in its domain, and then the function will also be continuous at that point. So if f of x is differentiable at a, then f prime of a exists. This means the derivative of the function at point a exists, and we know that the definition of the derivative is this f prime of a, which is equal to limit as x approaches to a f of x minus f of a divided by x minus a. We want to show that f of x is continuous at a point a by showing that the limit as x approaches to a f of x, which is equal to f of a. Thus we add and subtract minus f of a in this expression, and then we simplify this one. Again we multiply and divide x minus a with this expression, and here we have a new expression f of x minus f of a divided by x minus a into x minus a plus f of a, and we know that this is the definition of the derivative. We apply limit on this expression, and we get this expression, and this is equal to f prime of a, and this is equal to f prime of a, and we know that this is the definition of the derivative. And when we apply the limit on this function, on this expression x minus a, this will be 0, and here we have expression f dash of a into 0 will be 0, and we get this one. So as the limit x approaches to a, f of x that is equal to f of a, means when we apply the limit on f of x which is equal to the value of the function at a, and this means the given function is continuous at a. Okay, so and therefore since f of a is defined and limit of the function as x approaches to a which is equal to the value of the function at a, we conclude that f is continuous at a. Proved differentiability implies continuity. Continuity implies differentiability. We have proved differentiability implies continuity. Now we will see if a function is continuous, is it differentiable at that point or not. So we have example f of x is equal to mod of x. This function is continuous everywhere, and determine whether it is differentiable. So we know that this function is continuous everywhere. For any value of x, this function is continuous. There is no discontinuity. Okay, but at x is equal to 0, the derivative of the function is undefined, and we prove that this function at x is equal to 0, the derivative of the function is undefined. The derivative of the function is not exist at x is equal to 0. Undefined at x is equal to 0. So we know the definition of the derivative, that is f prime of x is equal to as limit h approaches to as h approaches to 0, f of x plus h minus f of x divided by h. We apply this definition on a given function and we simplify this, and we know that the mod of x is equal to under root of x square, and we apply this on this expression, and we get this one, and simplify this expression by multiplying and dividing by this one, and after simplification we get this expression, and that is equal to a derivative of the function, that is x divided by mod of x. So this is the derivative of f of x, and that is x divided by mod of x, and if we put x is equal to 0, and the derivative of the function will be undefined, 0 by 0. This is the undefined form. Okay, now we also prove this one by another by using other definition of a derivative. Okay, and or we apply this one, and this definition of the function f prime of a as limit x approaches to a, f of x divided by f of a. We applies this definition on a given function, and we get this expression as x approaches to 0, mod of x divided by x, and when we apply left limit and right limit on this function, we get a different value, that is -1 and +1. This is the left hand limit, and this is the right hand limit. Okay, right hand limit, both are not equal. Limit as x approaches to -0 of f of x is not equal to the limit as x approaches to +0 of f of x. Okay, so this means the slope of the tangent line will different for x less than 1 and for x greater than x less than 0 and for x greater than 0. Here we can see the slope of the tangent line. This is the slope. We know that the derivative of the function is equal to the slope of the tangent line. Slope of the tangent line. Now fail to differentiable at 0, this function f of x is equal to mod of x is fail to differentiable at x is equal to 0 because the limit of the slope of the tangent line on the left and right were not same. Visually, this result in a sharp corner on the graph of the function at 0. Here we can see that at x is equal to 0 we have a sharp corner. From this we conclude that in order to differentiable at a point a function must be smooth. At that point there should not be any sharp corner in the function. Okay, so we see this with the help of graph. We will see at x is equal to 0 the function is not differentiable. So here we can see that the function has a derivative when x is less than 0. When x is equal to 0, the function will be undefined. At that point the derivative of the function will be undefined. Here we can see that at that point the function have a non-derivative that is undefined, and when x is greater than 0 the function has a derivative. So now we have a Matlab code to plot a function, and this is the Matlab code to plot a function that we have discussed. Let us consider some additional situation in which a continuous function failed to be differentiable. Example: consider the function f of x that is equal to cube root of x, and we apply this definition on a given function, and we find the derivative of the function at a point. Okay, so we apply the definition of this function on this function at x is equal to 0, and we get this expression. And after simplification we simplify this function by multiplying and dividing by this one, and we get this expression as the limit x approaches to 0, 1 divided by cube root of x square, that is equal to positive infinity due to of x square. So at x is equal to 0 the function is not differentiable. The derivative, this mean the slope of the tangent line at x is equal to 0, that is infinite. Okay, so when the function have a tangent line with infinite slope, at that point the function is not a differentiable. So this is the function, this is the graph of the given function that is continuous everywhere. F of x is equal to cube root of x, and at x is equal to 0 the function has a tangent line with a slope infinite slope. This means at that point the function is not differentiable. So the function is continuous at 0 but not differentiable at 0. This means if a function is continuous, it does not imply the differentiability. It doesn't mean if a function is continuous it will also be differentiable at that point. Okay, at x is equal to 0 the function has a tangent line with infinite slope, and we can see if the x is increasing, the slope of the tangent line will also decrease. At x is equal to 0 the function has an infinite slope, but as x is increasing the slope of the tangent line is also decreasing. Let us consider another example, and we will see is continuity implies a differentiability or not. So we have example, consider the function that is f of x is equal to this one if x is not equal to 0, and 0 if x is equal to 0. Also has a derivative that exhibits interesting behavior at 0. So solution, this is the definition of the derivative. We apply the definition of the derivative on this function, and we will see that if a function is if a function is continuous, then is it differentiable or not. So we apply this definition on this function, and we have a is equal to 0, and we get this expression, and the derivative of the function at 0. Okay, so limit as x approaches to 0 sine of 1 divided by x, as we will see the behavior of the function when as x approaches to 0. So this limit does not exist essentially because when we substitute x is equal to 0 we will get infinity. So essentially, because the slope of the secant line continuously changes direction as they approaches to 0. So we see in the behavior of the tangent line, behavior of the slope of the secant line as the limit is approaches to 0 with the help of a graph. And this is the graph of a given function. This is of this function f of x, and we will plot a secant line, okay, between 2 points on, and we will see the slope of this secant line will changes continuously with positive and negative as x approaches to 0. So this is the graph of a given function, and now we see the secant line, and this is the secant line, and we see the slope of the secant line changes continuously as x approaches to 0. As x approaches to 0, the slope of the secant line is continuously changes. So this means the function is not differentiable at 0. Key concept: the derivative of function f of x is the function whose value at x is f prime of x. Yes, if the given function, we have a given function f of x, and the derivative of this function at x will be something, okay. So next we have the graph of a derivative function f prime of x is related to the graph of f of x, where the function has a tangent line with positive slope. The derivative will be positive. Where the function has a tangent line with the negative, the derivative of the function will also negative. And where the function has a horizontal tangent line, the derivative will be 0. So we can see this with the help of a example, and this is a function, and we can see that when the function is when the slope of the tangent line is positive, the derivative of the function is positive, and when the tangent line is horizontal to f of x, then the derivative of the function will be 0. We can see at this point the derivative is 0, and the slope of the tangent line is horizontal to the function. And when the slope of the tangent line is negative, the derivative of the function is negative. So next we have a third point: if a function is differentiable at a point, then it is continuous at that point. A function is not differentiable at a point if it is not continuous at a point, if it has the vertical tangent line at the point, or if the graph has a sharp corner.